Hello everyone, I am Natalia and I welcome you all to this session. Today's session is all about introduction to object-oriented programming concepts. Here is a quick overview of what we will cover in today's session. We will start by comparing procedural style of programming with object-oriented approach. In procedural programming, we focus on writing functions that operate on data, and in object-oriented programming, we shift that mindset. We package both the data and behavior together in entities called objects. So we'll discuss this in detail. Next, we will see what is the difference between programming language and paradigm. Next, we will understand objects and the four pillars of OOP that are encapsulation, abstraction, inheritance, and polymorphism. These pillars are what basically gives OOP its structure, flexibility, and power. Next, we will see basic class design. We will try to learn how to define member functions. And finally, we will put together everything by defining member functions and data members and how the whole object behaves, making our objects interactive, reusable, and meaningful in solving real-world problems. Before we dive into object-oriented programming, let's take a moment to understand why it becomes necessary in the first place. Let's look at some of the main problems with the older procedural style of programming. So in procedural programming, functions and data are separate. They do not model real-world entities efficiently. So we typically write a bunch of functions that operate on data, and the issue is that the data and functions that use it are kept apart. Imagine we are writing a program for a car rental system maybe, and we might have one structure storing the details about the cars like brand, model, and availability, and separate functions to return, rent, or service those cars. So the functions and data are related, but they are not connected. So this makes it hard to think about the program in terms of real-world entities. So real-world objects combine state and behavior. In real world, every object has two main aspects, state and behavior. For example, think about a person. A person's state might include its height, age, and mood, things that basically describe them. The behavior includes actions like running, sleeping, or speaking. Both the aspects belong to the same individual, so you can't separate them. But in procedural programming, we treat them as if they are completely independent, but that's not how the real world works. Another big problem with procedural programming is global data. When the data is accessible by many functions, any of them can change it. Sometimes maybe unintentionally. For example, if you have a global variable, for example, for storing the total number of available cars, one function might update it correctly, but another might accidentally reset it or maybe corrupt it. So this makes debugging and maintenance very much difficult because it is harder to track who changed what and when. Finally, poor scalability. That's adding new data means modifying many functions. So procedural code doesn't basically scale well. Let's say our car structure gets a new attribute, for example, GPS enabled flag. Now every function that deals with car need to be modified to handle this new change, this new property of GPS enabled. So as the programs grow, this becomes very unmanageable and error prone. So to solve these problems, object-oriented programming was introduced. Instead of separating the functions and data, OOP basically combines them inside objects. Each object keeps its own state and defines its own behavior. So in our car rental example, each car can be an object that knows its own details and has its own methods to return, rent, or service itself. So this approach basically mirrors the real world much better, and that's one of the main reasons OOP becomes so powerful. Now that we have seen the drawbacks of procedural programming, let's look at why object-oriented programming becomes so important. So OOP wasn't just a new style, it was a response to a very real software development problems, growing complexity, long development cycles, and maybe fragile system. So it reduces effort and complexity, number one. For example, in large procedural systems, adding new features or fixing bugs can be time consuming and error prone because of the tight coupling between the functions and data. So OOP reduces this by organizing code around the objects that encapsulate their own data and logic. So this makes the system easier to understand and modify and extend. For example, if you are developing a banking system, each component like account, customers or transactions can be an object. So if the logic of one changes, it's mostly isolated from the rest of the system. So this reduces ripple effects. Next is faster adaptation to change. Business environments basically evolve. New requirements, new regulations or new customer needs arise all of the time. So with OOP, systems can adapt more easily because objects are modular and they are self-contained. So you can update one class and then replace it entirely without rewriting everything else. So this agility means quicker response to change and shorter the release cycles. Next is the flexibility and reusability. So one of the greatest strength of OOP is reusability. Once you create a well-designed class, you can reuse it in other parts of the program or even in future projects. For example, a generic user class in one system could be adapted and reused in other application with minimal modification. So through concepts like inheritance and polymorphism, we can achieve that. So new classes can extend existing ones. So this basically saves time and reduces duplication. We will see this concept in detail once we reach the topic of inheritance and polymorphism. And finally, reliability. It increases reliability. So the main goals of OOP are to make the software development more efficient, flexible and reliable. Now that we know why object-oriented programming is valuable, let's explore how it achieves these goals, starting with its most fundamental building block, the object itself. So everything in OOP revolves around objects. So understanding them clearly is very crucial. Object is not just a piece of data or random set of functions. It's a combination of both the data that describes something and behavior that defines what it can do. So basically it combines data and behavior. You can think of an object as a mini capsule inside your program containing both its properties and the actions that belong to it. It represents real-world entities. So the goal of OOP is to bring our programs closer to the real world. For example, if you are building a car simulation, each car can be represented as an object. So the car object can hold details about the specific car and also know how to perform actions like maybe refueling or driving. That's what makes OOP intuitive. You can think about your program in terms of familiar real-world objects. The data representation relates to what the object is and what defines the object. For a car, it includes the color, model, speed, fuel level. So these are the object level and object attributes or properties, so they form the state of that object. Each car object might have a different data. For example, a red car and a blue car, but they share basically same structure. Then interface are basically your methods, how to interact with the object. This is done through obviously functions and methods that belong to that object. For this example, our car, those could be the methods like maybe start, accelerate, brake, refuel function. So you can think of these methods as buttons or controls that let us use the car. We do not need to know what's happening under the hood. We just call the method and the object takes care of the details internally. So in summary, an object combines data, that is its state, and methods, which are its behavior. So it mirrors a real world entity inside a program. Now that we understand the objects, that is are basically combination of data and behavior, the next question is, how are these objects defined and created? So in OOP, that's where the concept of class comes in. Objects are specific realizations of a class. So in real world, every object we see can usually be thought of as an example of some broader category. For instance, you and I are both examples of the class human. Each of us is unique. We have different heights, voices, and personality, but we share the same fundamental characteristics that define humans. So class basically defines the common pattern or blueprint. In object-oriented programming, this shared pattern is represented by a class. A class is like a blueprint or a template that defines what attributes and behavior its objects will have. It defines the general structure, but it's not a real tangible thing unless we create an object from this class. So basically, objects that are instances of a class share the same structure but differ in details. When we create an actual object from the class, that object is called an instance, and each instance follows the same pattern that is defined by its class, and it can hold different values for its attribute. For example, if a class is car, then two objects, say red Toyota and blue BMW, both have the same structure, that is maybe the model, color, speed, fuel level, but their details differ, their attributes differ. So as you can see, the idea of object applied basically applies across many fields, not just in code. For example, in graphics programs, shapes like points, lines, circles are all objects, each with their own data and behavior. In mathematics, object can represent maybe numbers or matrices, each supporting certain operations. And in computer user environment, objects represent things like the interface, things like windows, menus, and buttons that you interact with. And if you think about the data structure or data storage aspect, then objects can model structures such as arrays, stacks, linked list, and these all have their own properties and functions. So the object concept is universal. It helps us describe and organize and interact with almost any kind of entity, real or abstract. Before we dive deeper into object-oriented programming, it is also important to clarify something that often confuses many beginners and students. So let's see the difference between a programming language and a programming paradigm. So programming language is basically the tool, or you can call a medium. Programming language is simply a tool that we use to communicate with the computer. Each language has its own syntax, keyword, and rules, just like human languages. So for example, C, C++, Python, Java, or all of these are different programming languages, but they can all be used to solve similar problems. For example, think of it like speaking maybe English, Spanish, French, Urdu. The message can be same, but the form of expression basically changes. So programming language is basically a tool, or we can say a medium. Programming paradigm is basically the mindset or the approach. It's a way of thinking, a conceptual model for storing and solving problems. So it is not about the syntax, but how we design our problems. For example, procedural paradigm focuses on function and step-by-step instructions, whereas object-oriented programming focuses on objects and their interactions. Functional paradigm emphasizes mathematical functions and immutability. So paradigms are more about the philosophy of programming, you can say, rather than the language itself. So languages can support multiple paradigms. Here's where it gets interesting. Basically, most modern languages aren't tied just to one paradigm. For instance, C++ was originally procedural but evolved to include strong object-oriented features. Python supports both procedural and object-oriented styles. You can write plain scripts with functions or define classes and objects. So when we say OOP in Python or OOP in C++, we are really saying that we are using the object-oriented programming paradigm through those languages. So in summary, the language is a tool and paradigm is an approach. You can think of it like the language is your instrument and paradigm is your style of playing. So we have seen why the object-oriented programming is different, but what exactly are the objects we keep talking about? Let's explore what they are, how they work, and what are the 4 key principles that make object-oriented programming such a powerful way to think about programming. So these are basically 4 pillars of OOP. Encapsulation is basically this concept of one capsule, that is the data and methods. You group them into one unit and call it an object. So basically this concept restricts outside access to the object's internal state. Abstraction is about hiding unnecessary details and showing only what is relevant. For example, if we use drive function or a brake function for a car, we are just using this function without going into internals and technical internal details. So this way of hiding unnecessary details and getting only what's relevant is the concept of abstraction. Next important concept or principle is inheritance, and it is all about creating new classes based on existing ones. For example, if we have a common behavior that can be reused in other classes or objects. For example, as a human, we can be student, teacher, employee. So both of all of these 3 classes like student, teacher and employee share some common characteristics of human. So if we create a class of human, we can inherit from it or student class, teacher class and employee class. So we will learn more about it. So heart of this concept is about reusability. So it enhances basically code reusability. You create new classes based on the parent classes or existing ones. So this basically saves you from rewriting and it promotes reusability of code. And finally, we will also discuss this concept later on. Polymorphism is about objects of different classes to respond to the same function call in different ways. For example, we can have different types of vehicles like car, bike or a truck, and these classes basically share a common characteristics or behavior of vehicle. So we can make a vehicle class and inherit these 3 classes out of it. Now if we closely analyze the function move, then general movement characteristics can be stored at parent level like vehicle, and car, bike and truck have their own implementations according to their structure, specific attributes and specific method implementation relating to it only. Now that we understand what objects are and we have also seen the 4 pillars and 4 principles, let's look at how we design them in code. So in object-oriented programming, a class is a blueprint that defines the structure and behavior of its objects, and you can think of the class as a 3-compartment box. So in the top section you enclose basically the class name. For example, in this example, car is basically a class name. Then in the middle section, this holds the data members, also called attributes or states, that represent the properties of that object basically. For example, in this case, color, speed or fuel level relates to class. And then in bottom section it holds member functions. So the bottom section is all about the methods and behaviors. So these define what the object can do. Like in our example, a car can start, accelerate or brake. So these functions can be a part of this third bottom section. So this 3-part structure helps us in separating out data from the behavior in a very much clean and organized way, making things easier for us to extend and manage. Once we have designed the class, the next step is to define its behavior through member functions. So member functions describe what an object can do. They operate on the same class data members. For example, in C++ you can define these functions either directly in a class or outside using scope resolution operator. So we basically define the class with the class keyword, and then we have that curly braces that end with semicolon. Now let's start with access modifiers that are heart of the concept encapsulation. So first see the public modifier, the public members are accessible from anywhere inside or outside the class. They typically form the interface of your class, functions that other code will call to interact with your object. For example, in a car class, methods like start or accelerate would be public, because any code that creates a car object should be able to call those. Next is private, which is the most restrictive level of access. Private members can only be accessed by functions that are part of the same class. For instance, in this example that you are seeing, the variable speed is private. This means we cannot directly change it from outside the class. Instead, we must use a public function for example, like we have defined, maybe we will define a function accelerate to modify it. So this ensures that our object internal state is protected from accidental or unauthorized changes, so which is one of the main goals of encapsulation. So common approach is to keep the data members private and keep the member functions public, so other things like different functions or other objects outside the class can use it. In object-oriented programming, access modifiers basically determines the visibility of data members and functions within the class. So they are essential part of your encapsulation concept that we just covered. So they help us control what part of the object's data or behavior can be seen or changed by other parts of the program. Then there is also a third access modifier, protected, which we haven't covered yet, as it relates to inheritance concept. So we will cover it when we are going to discuss the inheritance. So protected is basically a middle ground between public and private. Protected members are not accessible from outside, but they are accessible from the derived classes. So we have parent class and then inherited or derived class concept. So they are accessible by the derived classes. For example, we later create a class electric car that maybe inherits from this created car class. So it will be able to access mileage because it's protected, for example. So we will explore this concept more deeply once we discuss inheritance, but for now just remember that protected allows access for child classes. Now that we have seen how the modifiers work, let's see how they affect the way we interact with objects in program. In this example, you will see we have defined start function inside the class body. So there is another possibility that we might define some function, declare function inside the class, but define or its body must be given maybe outside the class. So in this case, for example, the break function you are seeing in this example is not defined and declared both in the class. It is only declared inside the class. So in order for this function to define outside the class, we must enclose scope resolution operator, the two semicolons basically that are highlighted for your reference, before the function name. So I will be writing return type, that is void, and then car class name and scope resolution operator. So the function name must be preceded by a class name and scope resolution operator if we intend to declare it inside the class but define it outside the class. Now that we have seen how access modifiers work, let's see how they affect the way we interact with objects in a program. When we define a class, we are essentially creating a blueprint. So the class defines the structure, the data and functions, but it doesn't actually create anything by itself. So to create a usable object, we must instantiate it. That means we create a variable of that class type, just like you can see in this example, car C1. Here car is the class name and C1 is an instance or object of that class. So once we have an object, we can access its public members like methods or attributes using dot notation. For example, we can see the call C1.start. It executes the start function belonging to that specific object. So this dot notation works just like accessing attributes of real-world entities. You might think of it like saying car number 1 start. We are addressing a specific object and asking it to perform one of its behavior. So it is important to note that only public members can be accessed this way. If we try to do something like, for example, speed c1.speed is equals to 100, the compiler would throw an error because speed was declared as private, and we have intentionally hidden it to maintain control over how it is modified. So in that case, you cannot access private members outside the class, so it will throw an error. So this is one of the strengths of OOP. We interact with objects using public interface while keeping their internal data secure and consistent. So the combination of access control, object creation, and that dot notation gives us a structured and safe way to represent and manipulate the real world entities in one code. So let's look at an example to reinforce what we have just learned about the classes and access modifier and the object interaction. Here we have defined the class car with private member as data member as speed, protected member as mileage, and some public methods, two public member functions named start and accelerate. So once in outside the class, maybe in the main function, we try to create an object like car c1, and then we have the second line is c1.start. So this is basically allowed as start function is declared as public, so it is accessible everywhere. But you will notice that once we try to write c1.speed or try to change or access speed using dot notation, it will throw an error. So it is not allowed, as we have just discussed that it cannot be accessed directly from outside the class since it's declared as private. And also this also goes for protected, by the way. For protected, the only relaxation is of access is given to child classes. So in this example, we are not dealing with any child classes, so this will throw an error once we start to write statements like c1 dot mileage is equals to 30 or 20. So this basically helps us to maintain control over how the car is set or changed, and this is another example of encapsulation in action. Let's look at another example to reinforce again the encapsulation concept. Here we have defined a class named line. So class is just like a template that describes the properties and behaviors of a particular type of object. So in this case, the class models a simple concept, a line with a certain length. So notice that inside the class we first have a private data member of type integer. Because it is private, again it cannot be accessed directly from outside the class. Next we have two public members named setLength and showLength. So these provide controlled access to private data. SetLength takes an integer value and assigns it to length, and showLength simply returns the stored value so that we can display it later. So by doing this, we make sure that all the changes to our data go through proper channel. We never expose length directly. We have added relevant public functions to perform the calculations and manipulations. For example, we have added another public function multiply by 2, which performs a simple calculation based on the data. It multiplies the length by 2 and displays the result. So this shows how member functions cannot only access private data but also perform useful operations. So these public function defined inside the class can access private data, but if we are standing outside the class and trying to access private members, then we are not allowed. So in the main function, we create an object of line class named L, and this line L basically allocates memory for one specific line object, which now has its own private length variable inside it. We then call the public functions using dot notation. L dot set length 6. This basically sets the internal length to 6. So thank you for your attention and participation. I hope this session gave you a solid foundation for understanding classes, objects, and their role in building maintainable systems. In the upcoming session, we will dive deeper into how objects are born and destroyed, how they are created, clean up using constructors and destructors. So I'll see you in the next session. please don't forget to subscribe if you are interested in going deeper into object-oriented programming.